Assalamu alaikum wa rahmatullah, and thank you very much. And it's a great pleasure and honor to welcome all of you to this webinar titled Bonded Joinings Using Reversible Adhesives. So I'm personally very much excited to present this topic, and this was supposed to be scheduled before our break, but due to some issues, we could only present it today. And I personally apologize for that. And in fact, I'm really excited to present this one as this particular project, it got us lots of recognitions in terms of a generous funding of few $1 million, few patents, and also significant number of publications. Also, it is one of the most exciting work that I've personally carried out during my doctoral and postdoctoral period. Now, before I dwell into the topic, I would like to reinforce what do I mean by structural joinings. All of us in our day-to-day life, we see many structures, maybe like a chair that we sit on, or like a table, or like the car that we travel. And all these structures, they are made of different number of parts. For instance, like the car that you travel, it may have approximately around 25,000 to 30,000 different parts. Or if you think of the largest commercial airplane that we have, Airbus A380, it has nearly 4 million parts. So in order to make it as a single functional structure, you need to have a mechanism or a technique to combine all these different parts. So structural joinings, that is what we meant by structural joinings. And bonded joints, bonded joinings is one of the structural joining technique. And I want all of us to take a little pause and just think of the largest structural joint that you can think about, the standalone largest structure without any structural joints. I just want to repeat it. Just think about the largest structure without any joints in it. And in fact, I asked the same question in my classroom, and some of the students, they came up with an answer: cast iron skillet. That is the largest structure or a part that they can think about without any joints within them. So the idea behind this question is not to tickle your mind, but rather it is to emphasize the importance of structural joinings in our day-to-day life. So now, joining, as I just said, like it's key and critical aspect in design of any structure and in manufacturing. And every joint interrupts structural geometry, thereby creating material discontinuities, problem of load transfer, local peak stresses, and contributions to vehicle noise and vibrations, and so on. And all these issues get worse when we go for multi-material joinings. And that is what is happening even within the aerospace. If you can think about like an aerospace vehicle, it constitutes like hundreds of different materials. And these materials needs to be joined together. So all these issues needs to be tackled when you go for a structural joining technique. And generally speaking, the joinings can be divided into three main categories. That is mechanical fastening, you have adhesive bonding, you have welding techniques. And out of all these techniques, mechanical fastening is I can call it as the most understood or most explored techniques out of all these three. Nevertheless, they say nearly 1 million holes are drilled, because if you want to do the mechanical fastening with respect to bolts or rivets or fasteners, you need to drill holes on the plates. And just in Boeing alone, they said they drill nearly 1 million holes in one single day. So this is labor intensive. It is expensive, and with the advent of composite materials, it drastically reduced the strength of the structure. So also it doesn't. Also, these fasteners that if you think like these are metallic fasteners, it adds weight And once you drill holes in the composite structures, it introduces stress concentrations, delaminations, and so on. Now, in bonded joints, there is no drilling process. So that is one of the major advantage of it. And there is a relatively uniform load transfer across the bonded region. So let me take the pointer options here. So if you can see here, instead of a bolt or like drilling a hole, like you just simply have an adhesive to bond them. So there is no drilling process here, and the load is more uniformly going across this particular adhesive. But the issue is, the conventional adhesives that you make using the thermoset polymers, they are weak. I mean, the thermoplastics, they are weak. The thermosets are relatively stronger. And the issue with the thermoset polymers is that they are one-time cure. The conventional thermoset polymers, they are one-time cure, and you cannot disassemble it. Unlike the mechanical fastening. In mechanical fastening, once you try to assemble something, you can disassemble in case needed. Like, for example, if you want to do some repair or maintenance, you can still disassemble the components by debolting it. Whereas if you make a bonded joint using thermoset as adhesive, you cannot do the disassembly or like debonding. So reversibility is one of the major constraints in adhesive bonding. And the immediate solution that we can think about is by using a thermoplastic polymer because it is reversible in nature. The issue is also, in order to join two components using thermoplastics, you have to heat them within an oven, because the conventional thermoplastics, that is the only way that you can heat a thermoplastic, conventionally speaking. So that is another issue with incorporating thermoplastics for structural joining. And if you think about larger components, if you want to join two huge parts, then you need to make a larger oven where you can put both the components, including the adhesive. So this is not a viable technique for manufacturing using thermoplastic adhesive. So our idea was to incorporate the advantages offered by both the techniques. In mechanical fastening, it has an advantage of doing the disassembly. And in adhesive bonding, it has an advantage of not drilling any holes. So can we have a joining technique that can facilitate the advantages from both this technique? So we thought of developing a separate adhesive called reversible adhesive and use a different heating technique other than thermoplastics, other than the oven, the conventional oven. And that is electromagnetic induction heating technique. And according to this technique, any conductive particles or any conductive object, if placed within the changing magnetic field, heat will be generated by means of Joule's effect or by hysteresis. So in a typical induction heating system, an AC power is supplied through the conductive coil. The red coil that you're seeing is a conductive coil, and AC current is supplied to that. This generates an alternating magnetic field around the coil. And if you place any conductive piece within this magnetic field, it induces an eddy current within this conductive material. And the resistive heat loss due to this current, we call it Joule's effect, that heats up this particular material. Now, if the workpiece material is magnetic, in addition to conductivity, it is also magnetic, then there will be an extra heating source, that is hysteresis loss. Now, the question is how to make the thermoplastic polymer conductive, because we know that the thermoplastic offers the reversibility. We cannot use the thermosets. And thermoplastics are insulators. So because they are insulators by nature, we reinforce these thermoplastics with conductive nanoparticles. Now, these nanoparticles respond to the EM radiations. So if you see here, I have my substrates or the components to bond. and I have my adhesive here. So if I have any conductive particles reinforced within two thermoplastic polymer, then each of these nanoparticle will act as nanoheaters, and they heat the surrounding polymer, and eventually the polymer will melt and it flows between the two substrates, and we can bond them. So that is the concept of electromagnetic induction heating. So it is a rapid heating technique, and it is highly energy efficient because this heats up in a matter of a minute. Whereas if you go for conventional oven bonded joinings, it takes nearly half an hour to 45 minutes if you want to make one particular joint. So that is one of the major advantages, like you save a lot of energy. It is a selective heating. For instance, like if you want to join two different composite materials, and if you expose this particular joining assembly for EM heating, it is a selective heating. In other words, it heats only the adhesive in between the substrate, and you get an optimized consistency. So these are like the different advantages offered by this technique. Now, here are some of the technical gaps given by the Ministry of Energy, the US Department of Energy. And some of the gaps that they have mentioned is lack of technology for joining dissimilar materials. So this is one of the major concerns. And also experimentally validated models and simulations. Yes, we come up with lots of computational models and so on, but are they experimentally validated? And also efficient and rapid manufacturing and repair. So you can have a technique, but can you do the disassembly in a quick and rapid fashion? So this can reduce the lead times in the manufacturing industries by a significant figure. Now, the goal of this work is to characterize the reversible adhesives and develop experimentally validated computational tools for the better design of bonded joints. So as such, I will be presenting the different factors, or like the different stages of this particular project within it. That will include development of reversible adhesives, bonded joints manufactured using reversible adhesives using electromagnetic induction heating. I'll also talk about the micromechanical modeling, multi-scale FE model, and also there will be a section on the residual stresses developed within the bonded joints due to the manufacturing. Now, just to give you a heads up of the materials used within this project, they are thermoplastic polymers. I'm using a thermoplastic polymer as an adhesive, that is acrylonitrile butadiene styrene, so ABS. The reason why I use this particular adhesive is because this was readily available in our lab, and this had like significant applications in many of the automotive sectors. So we picked up this particular thermoplastic polymer. Just to give you a note that we can use any other thermoplastic polymer to make a reversible adhesive. And the reinforcement, so we need conductive reinforcement to activate this thermoplastic with respect to EM heating. So for that, I use two different kinds of reinforcement. The first one is ferromagnetic nanoparticles and also short carbon fibers. The reason why we use ferromagnetic nanoparticles is because like they are conductive and at the same time magnetosensitive particles. In other words, they can produce heat by means of eddy current and also by means of hysteresis losses. And the second reinforcement is the short carbon fibers. This mainly produces heat by Joule's effect, and they enhance the mechanical properties a lot. So although the thermoplastic polymer, they are inherently weak than thermoset, by reinforcing them with these particles, they not only allow us to heat the thermoplastic with EM heating, but at the same time, they enhance the mechanical properties of the adhesive. Now, I just want to show you a small demo of how it works. So over here, you will see a bonded joint. So the white color substrate that you're seeing, they are glass fibers. So they're glass fiber composite bonded using reversible adhesive. And you have an EM coil here. And just do not blink your eyes because this will be much faster. Just wanna get out of the full screen mode too. So you see that it's a very quick process. In a matter of few seconds, you can debond any components, and it is a non-contact debonding technique. So just to show you one more time. It literally took 3 seconds to debond 2 composite substrates. So we can think about the different airplane junkyards or like the structures which are towards the end of their lifetime. Once you have it bonded using reversible adhesive, you can reuse them, or you can debond or disassemble these components, and you can use it for some other purpose. So these are like more of green structures, or like environmental friendly structures could be manufactured using this particular technique. Now, the approach of this particular project is integration of both the experiments, and at each scale, we have experimentally validated computational models. For instance, like over here, like you have the reversible adhesive tensile coupon, and this is the fracture surface of it. And you can see there are like voids trapped in, and you have nanoparticles of ferromagnetic ferrites, and you have micro to nanoparticles of carbon fibers. You have short carbon fibers and also some other nanoparticles embedded. So all of them as a cluster. So we have computational models that takes into account all these heterogeneities, and we run these simulations, and eventually we get the material constitutive behavior from here, and that will be fed as the material properties for the adhesive in a macro scale in a lab joint. And eventually you can have experimentally validated models to optimize different factors with respect to your design. Now, just want to give you a presentation overview. So the first step will be how did we manufacture this adhesive, and what was the different characterizations that we took it. And also then the second step is the reversibility and degradation. So we call it reversible adhesive. So to what extent we can reverse it? How many heat cycles can it withstand before it completely loses its mechanical properties? And to what extent it degrades? So that is the second step. And in the third step, I have a characterization study based upon bonded joints. So we made bonded joints using both oven heating and electromagnetic induction heating, just for a comparison purpose. And we compared its properties, the mechanical properties. And we did different surface treatments and some other studies to see like how we can improve the bonded joint property. And also the fourth stage of this presentation will be a computational model, where we address like how can we develop a computational model, in fact, a multi-scale computational model, where it takes into account all the material heterogeneities in a material scale, and that properties will be taken further for the macro scale simulation. And also the fifth stage will be the healing potential. So yes, these bonded joints, once after they manufacture, they undergo several loads, and there can be some existence of the flaws within the adhesive. Can we heal these flaws or defects within the adhesive to regain its inherent strength? That is the fifth stage. And the last stage is like the residual strain monitoring. Can we monitor, or can we predict what is the amount of residual stresses developed due to this particular manufacturing techniques? So this is just an overview of this presentation. So let's get into the first step, that is the adhesive processing and characterization. So as I said, we have used ABS as the thermoplastics that you see over here. And we have like 2 different nanoparticles. And we used a DSM micro extruder to manufacture the reversible adhesive. So what we did here was that we fed into this extruder a combination of both the ABS pellets mixed with the right weight percent or the volume percent of the nanoparticles. And the extruder is at a temperature that is at the melting point of ABS. So once you feed this mixture, all this mixture will get grinded by these twin screws, and it gets grinded like at the melting temperature. So you will get a molten mixture as an end product. And this molten mixture will be taken into a compression molder or into a die to make the required shapes that you want. For instance, here you have an impact coupon, a notched impact coupon. These are for impact testing. And you have a tensile coupon over here. And you have a film disc. These discs are mainly used to make the adhesive films for our bonded joints. So you can see over here like the different samples. So we have prepared, like, I'm sorry, like all of them are in the same color, but they are made of different weight percent or volume percent of ferromagnetic nanoparticles and carbon fibers. And going into the mechanical properties, you can clearly see that ferromagnetic nanoparticles, they are basically spherical in nature. So the enhancements of mechanical properties is very limited with this particular nanoparticle. You can see like hardly some increment was observed with respect to neat ABS when we went to 16 weight percent. Very little improvement in the tensile modulus. Whereas like if you see over here, once I add a 15 weight percent of carbon fiber, it increased the tensile modulus by 25% because the carbon fibers have a higher aspect ratio. They are not spherical in nature, their aspect ratios are much higher. And that means it can carry much more loads in an efficient manner than ferromagnetic nanoparticles. And another observation that we have seen with respect to mechanical testing is that the toughness reduced significantly as you increase the volume content of nanoparticles within the ABS polymer. And this was expected with respect to ferromagnetic nanoparticles. As you increase the number of content of these nanoparticles, each of them may act as a cause for stress concentration, and that may result in a quick failure. So that is one of the reasons. And yes, so we have manufactured the adhesive. Now, how to understand their response with respect to electromagnetic induction heating? So to understand their thermal response, here on the blue color that you see on the right-hand side, these are the adhesives. And we actually put distributed fiber optic sensors in between the adhesive. It's difficult to visualize it over here, but you can see some wires coming out from there. And these wires are actually the optical fiber sensors. And these were sandwiched by adhesive films. And these were placed within the EM coil. So once you switch on the EM coil, the reversible adhesive starts heating up. And these optical fiber sensors, they sense the temperature. So you can have different sensors like temperature sensors, but most of the temperature sensors that are available in the market, they can only catch the surface temperature. The idea behind using this kind of optical fiber sensors is that they can actually be embedded within the material, and these are like of very small diameters. Some of them are like 0.2 millimeters. And what we have used here for temperature sensing is like 1 millimeter diameter of the sensors. And they accurately give us a dynamic temperature results. For instance, like if you come to the left-hand side graph you can see on the y-axis, it is the temperature, and on the x-axis, you have the time, and you have a reversible adhesive with different weight percent of ferromagnetic nanoparticles. When you have smaller weight percent, you can see that it takes longer time to reach at least 100 C. And it doesn't even go to the melting point of the ABS. So, but we just wanted to try like what is the optimum weight percent. And when we increase the weight percent, for instance, like when we go to the 8 weight percent, yes, it reached nearly the processing temperature of the thermoplastic. By the way, there is no specific melting temperature for thermoplastics. We call it processing temperature. And the processing temperature of a thermoplastic can be in a range. And for ABS, it is anywhere between 200 to 240 C. So it took nearly 250 seconds to reach that temperature. So, but when we went to 12 weight percent or 16 or 20, it was immediate. Like we can get into the processing temperature within a range of 30 seconds. So it was much quicker. And also we have seen in the previous graph that 16, 12, 16, and 20, they gave us the best stiffness for the adhesive. So it was decided later that only 12, 16, and 20 weight percent of FMNP in ABS were considered for making the bonded lap joints. Now, the next set was reversible degradation. Yes, we know that these adhesives can be reversed. Now, to what extent you can expose these reversible adhesives to the EM heating? Or how many cycles of heating and cooling can it withstand before it fully degrades or before it fully loses its mechanical strength? To understand that, we need to expose the reversible adhesive to EM heating multiple cycles. And also we need to understand until what temperature this polymer it can keep its integrity in terms of mechanical strength. So for that, we actually developed a non-conductive ceramic mold, and you can see the mold over here. And this mold, we carved out the right specimen shape, the dog bone shape of the tensile coupon, and also the impact specimen coupon. And so once you expose them and once they melt, they start flowing. So you still keep the shape of the coupon. So once you cool them back, they will still keep the same shape. So you do not have to worry about losing the shape of the specimen. And once we expose them to EM heating, we saw a specific pattern. So you can see here a small degradation pattern, like we call it like a thermomechanical degradation because of the EM heating. And we did not know like what is the exact reason for this. Is it because of is it a degradation pattern that we even see in the oven heating? So we had to compare. So when we did the comparison, here is the cross-sectional view of the baseline that we got it like immediately after the extrusion process. And here I have the oven heating, like the material after the oven heating. So you cannot see any sort of degradation over here, but you can clearly see the degradation after the electromagnetic induction heating. So we call it voids because it was clearly some kind of voids. So now how can we understand this degradation better, or like to understand the causes of this particular degradation? So that was another issue that we wanted to study. So we thought of doing the repeated heat cycles for 3 times. So there will be like 3 repeated heat cycles to 240 C, because 240 C is like the temperature at which we process the adhesive. And at each heat cycle, we carried out the tensile and the impact testing to understand is there a degradation with respect to mechanical properties. And also we did a TGA, the thermogravimetric analysis, to understand at what temperature the polymer fully loses its constituents. And we measured the 1%, 2%, and 5% mass degradation. At what temperature do these things happen? And also wanted to see, like, at 1% mass degradation, what is its mechanical property? At 2% and 5%, because sometimes there is a possibility that, like, your EM heating may extend over 240C. And so when you go beyond 240C, what will happen to the mechanical strength? So these were the studies that we conducted. So this is the TGA graph on the left-hand side. On the y-axis, you have the weight percent, and on the x-axis, you have the temperature. So you can clearly see, like, by the time it is around 375C, it fully started losing its weight. So that means, like, you're degrading the polymer, or like this is the onset degradation temperature, like at which, like, you degrade most of the polymer. And on the right-hand side, you have the EM heating. So I took a ABS with 16 weight percent of ferromagnetic nanoparticles and exposed it to EM heating continuously. And by the time it reached 60 seconds, it reached nearly 372C. And I could not increase the temperature of the adhesive. Why? Because it is approximately at this range, you will see full degradation of the polymer. And you can see, like, the degradation even starts by the time it is 320C. And in fact, it is at 320C, like, it will start losing its weight and mass considerably. So you can, I just wanted to show the cross-sectional image of the adhesive, the tensile coupon, at different temperatures when you're subject to EM heating. So you can see, like, by the time it is, like, exposed to 370C, it is fully degraded. So we need to have an optimum EM processing so that we avoid this kind of degradation within the sample. Now, what is the effect of this heat treatments onto the reversible adhesives? So on the y-axis, you have the elastic modulus, and here you have the toughness or the strain to failure. And you can see that the elastic modulus is kind of consistent as it moves towards the higher temperatures, because it's not the polymer that was responsible, or the monomer that was responsible within ABS was still in place, but it was butadiene, that is the monomer that was responsible for the toughness. And once that gets reduced, then you really drop your toughness properties. And in fact, the acrylonitrile and styrene was still in place to some extent at this particular temperatures. And you can clearly see that nearly 40% of the toughness was reduced when you go beyond the processing temperatures of the ABS. So this was something that we need to avoid when you make the bonded joints. And here is the FTIR Spectra, where you can clearly see by the time you go to very high temperatures, you can see a drop in all the peaks. In other words, you can clearly see losing the polymers, which are responsible for the mechanical properties. So the red line that denotes the 370C, you can clearly see a huge degradation with respect to all the peaks. Now, if you look into the different heat cycles, for instance, like the processing temperature is 240C. So at 240C, I did different heat cycles. Just heat it to 240C, let it cool, do the mechanical testings. And we can get at different heat cycles what is the elastic modulus and what is the tensile strength. So you can see that the stiffness increases as you increase the heat cycles, but your strength remains almost the same, and the toughness reduces even if you are within the processing temperature. That is because, like, again, we clearly saw the losage of butadiene, and that means, like, the toughness is reduced, and as you loses the toughness properties, you automatically increase the stiffness within the polymer. Now, coming back to the degradation pattern that we have seen, so that rectangular pattern. So we were like little curious, like why exactly this particular pattern was produced when it was subjected to EM heating. In fact, there is something called skin effect in EM heating. So under electromagnetic induction heating, you only heat on the surface of the conductive particle. And if you think about this particular sample, then the surface is not here, the surface is right here. But because of the fluid flow within the die, you have most of your nanoparticles will be towards the center. And so what we did was to understand what is the weight percent of ferromagnetic nanoparticles around the cross section or across the cross section. We did a mass spectroscopy. We call it laser ablation inductively coupled mass spectroscopy, where you can use that technique to find out what is the amount of nanoparticles at different points across the thickness. And we found that you have the maximum number of points, I mean the maximum weight percent around this point, around this degradation pattern. So you can see that in point 2, you have 34% of ferromagnetic nanoparticles. And that is the reason like you got the skin effect around that region. And if you go beyond that, the weight percent of the nanoparticles is like 6.7. So that is not sufficient to create the EM heating. So that's the reason like you got the skin effect at this particular region. Now, when you do the processing, how can you avoid this kind of degradation? So we did different heating studies, like we heated it to 240C, and then we still found some of the degradation patterns. So we reduced the heating temperature, and we found that at around 180C, there are no degradation. And the polymer glass transition temperature is like around 105. So you can still get a very soft, nearly molten stage at around 180C. And we thought of a step control heating. So this way, you do not have any kind of degradation across the section. So you get the polymer in its inherent strength. Now, the next stage, once you have a controlled EM induction heating, then we use that technique to create the bonded joints. Now, to create the bonded joints, we again had to develop our own fixture to make a single lap joint. So this is the fixture that you see here. And the entire fixture must be made with non-conductive materials, because like if you have a conductive material, everything gets heated up, which are subjected to this EM coil. So all of them were like manufactured with non-conductive materials. And you can clearly see that this is before the lap joint processing. You can see some clearance. So after a few seconds of exposure, you can see that the clearance was reduced. That means like the upper adherent came closer to the lower adherent because the polymer got melted in between. And we kept some spaces of 0.5 millimeter. So this makes sure that the final adhesive thickness is like around 0.5 millimeters. And we also made single lap joints using oven heating. So one of the biggest drawback of oven heating is that once you expose even the components or the adherents will also get degraded. So you can clearly see like a darkening of the adherents over here. That means like even the adherent got degraded. And over here, you only heat the adhesive. So you still keep the original properties of the adherents with respect to electromagnetic induction heating. And there were several studies in terms of bonded joints. One of them was, can we do the oxygen plasma treatment? So if you do the oxygen plasma treatment on your adherents, you actually increase the surface energy for adhesion. So that will give you a better adhesion between the adherents and the adhesive. So over here, you will see OB denotes the oven bonded and IB denotes the induction bonded. So PT is the plasma treated, and you have pH that is preheated. Preheated in the sense like you can, yes, in our induction bonded joints, you only heat the adhesive. But we found another technique that if you don't preheat the adherent, you do not get much strength with respect to induction bonding. But once you preheat the adherent, not too much, but just to the glass transition temperature, that is like nearly 100 C, then you can considerably increase the strength of the induction bonded joint. And we got 15% better strength with induction bonded joints compared to the oven bonded joints, and a very good toughness as well. And the next study was a computational model. I can only give you a very brief of all these techniques. Why? Because the time doesn't permit for me to go in detail. So in the computational model, as I said, like we even took the material heterogeneities into the account. So for instance, like we had hybrid nanoparticles sometimes, like as a mixture of nanoparticles and short carbon fibers, as you see here. And we created an RVE using a computational software called DigiMat, and we got the homogeneous stiffness of this material, and that particular material value was given as the input for the large scale single lab joint. So here is the finite element geometry. How does it looks like? So you can see that these are ferromagnetic nanoparticles, and you can see the chopped short carbon fibers. And there are also voids. Sometimes you see like you have, if your material is degraded, then you can also simulate that. Like once you calculate the right amount, what is the exact amount of these particles and everything, then you can feed the exact volume percent of the voids or the particles and everything, that you can create the RVE. And once you test them, you can get the material constitutive behavior from there. And we also used an interface modulus. So for instance, if you come over here, you can see that the particle, the ferromagnetic nanoparticles, is like actually this ash white in color. And the green outer surface is actually the interface. So in nanomechanics, when you have polymers and nanoparticles, there is a region just outside the nanoparticles, and that region will have neither the properties of the nanoparticles nor the properties of the polymer. The properties of that region is somewhere in between. So you need to account for that particular region as well. So we actually created an analytical model based upon another study, and we incorporated that model as a UMAT or material subroutine to the software to get better accuracy. This is the model that we had. And here is the finite element model. Here's the geometry. And here is the finite element model. How does it look like? It's a very complex model, especially like when you go for this entire particular geometry is like in 1 microns by 1 micron. And the interface region is very thin, and like you still manage to get like at least 2 to 3 layers of meshes within the interface. And the way, because like once you do the experimental observation, so this is a scanning electron microscopy image, and you can see that the carbon fibers that you got over here is of different length scales. And how can we get an average length scale? So we did a log normal distribution, and we found that the average aspect ratio of this short carbon fibers is like around 4.6. And another observation that we have seen is this nanoparticles, they cluster together. And we found that an average clustering diameter is like around 300 nanometers. So these were the data that we got using the experimental observation, and then we gave this particular data to the computational simulation. So here are some of the analytical model results. And this is how a scanning electron microscopy looks like. So you can clearly see like the difference between the short carbon. This is one of the short carbon fibers, and its diameter is like around 8 micron. And you can see the ferromagnetic nanoparticles. These are like 100 nanometers, much smaller in size, but they are still hybrid composite because you have like, these are two different reinforcement within ABS. And we had to model them separately. So we had a nanoscale model where you had only the ferromagnetic nanoparticles, and then we got the equivalent property of this one, and we fed that as the matrix property when we had the short carbon fibers, when we went to the micro scale. And then we analyzed this particular RVE to compare it with the experimental value. So you can clearly see over here. So we got a good comparison with the experimental value, and nearly the interface thickness was found to be around 40 nanometers. And you can clearly see like a very good comparison within less than 5% error was found between the experimental and computational models. And that particular constitutive behavior was fed as the adhesive property in our single lab joint that we created. And we got a really good comparison with the macro scale as well. The next study that we did with respect to this particular project was to find out the healing potential of the bonded joints. Now, if you think about bonded joints, as I discussed before, this can be subjected to different kind of impacts or external loadings, and that will result in the flaws or the defects within the adhesive bond line, and you can clearly it clearly manifests the drawbacks or the drop of the structural efficiency. Now, can we repair this particular adhesive defect by exposing them to different heating techniques? So we have found out that once you have this kind of defects, then you can expose them to the EM heating, and this polymer get reheated and they fill the gap again. So you can heal this particular defect, and you can regain the strength to some extent. I'm not telling like you can regain the 100%, but a significant strength could be regained. You can see over here. So you have the baseline structures. In the baseline, like you have the left-hand side, you have the load to failure, and this one is the displacement to failure. And after the impact, you reduce both the load to failure and the impact and the displacement to failure. And once you expose them to the heatings, like you can either heat by induction technique or by oven technique. Definitely we can go for induction heating. Why? Because this is much more faster, and you can do the repair much faster and rapidly. And this is something that the industries are looking for. Over here, like we healed the bonded joints in a matter of 50 seconds. And over here, like we healed the bonded joints in nearly 1 hour. So you can clearly see the lead time reduction, because once that is one of the major constraints even in aerospace that we are facing. Like if there are some issues of repair or maintenance, it takes a lot of time for the customers to get the airplane back, because they need to make sure that the healing procedure was properly satisfied. So after the healing process, nearly 92% of the strength was regained, and 81% of the displacement was regained. So it's not a 100% recovery, but still it's a decent technique. And the rest of, and you can ask like what happened to the other strength? Because if you go back to its original structure, like because of the impact, the transverse impact, even the adherent was affected. It was not just the adhesive. And with this particular heating technique, you can only heal the adhesive, not the adherent alone. So once you do the maintenance for the adherents, then you can get the full recovery. But in this particular study, the objective was only to heal the adhesive. Now, residual strain monitoring. This is another important aspect that we need to take into account, because most of the time when you do a computational model, we assume that when you made a structure, there are no residual stresses developed. But that is a huge assumption, because many times, especially when we did this particular project, we found out that the amount of residual stresses presented within the structure is huge. It's like approaching nearby the yield strength of the adhesive. And so this study was mainly to, because there were no effective technique to monitor or to quantify the residual stresses developed in bonded joinings. So we thought of doing a combination of experimental and computational study to predict and to monitor the residual stresses within the bonded joints. So what we did was we used a optical fiber sensor, and the sensor is like nearly 0.2 millimeters in size. And this sensor was placed within the adhesive. So you can see that the sensor go within the adhesive. And we found out that for ABS as the adhesive, when you do the stresses, the residual stresses will start develop only when it reaches the stress-free temperature. So what is a stress-free temperature? So when you heat the structure, you heat it to 240 C. And once you start cooling, then when it reaches one particular temperature, it starts developing the residual stresses. So in terms of ABS, 120 C is the temperature at which the residual stresses starts developing. So we actually made the lap joint, and we had the optical fiber sensor within it, and we heated and we made the lap joint. And when it was about to cool, we used a particular fixture and we put the lap joint on the fixture and we let it cool. From 120 C onwards, we started monitoring the residual strains, because you cannot measure the stresses, but you measure the strains using the optical fiber sensor. And from the strains, what we did was we actually made a computational model, and that model was experimentally validated by matching the strains that we observed using the experiments. And then using the computational model, we can see what was the magnitude of residual stresses within the adhesive. So that was the plan. And yeah, here is the real lab joint that you can see that the fiber optical sensor is here. And this is the time once the adhesive has reached 120 C, and it will be monitoring the residual strains. And we actually did the cooling process in 3 different stages. One was the controlled cooling to the room temperature, and we also did uncontrolled cooling to the room temperature, and we did uncontrolled cooling in freezing chamber. So when I say controlled cooling, that means like we cooled the joint within the oven. We asked the oven to cool it by 5 degrees Celsius per minute, something like that. And in uncontrolled cooling, we just let the atmospheric temperature to act there. And in the uncontrolled cooling in the freezing chamber, we actually put the entire joint assembly inside a freezing chamber, and we let it cool. And we got a really good comparison between finite element model and experimental results. And what we have found from this experiment is like there is a 40% increase in the stresses, and the stresses like what we got within the adhesive is like nearly 40% of its tensile yield strength. So that is considerable. So when you really do a computational model, you need to account this particular residual stress that was developed due to the manufacturing. And that will give you much better accuracy in predicting the life of the structure. Now, to conclude, at least 8% of ferromagnetic nanoparticles is essential to have a percolation limit that will lead to the rapid melting in the ABS polymer if you're going with electromagnetic induction heating. And also the process monitoring suggests that the temperature shouldn't exceed 180 C to ensure that the degradation does not occur. In the joining process, it is essential to surface treat so that it remove the low molecular weight surfactants and make the joints much more stronger. Like, so many times, like there will be surfactants present on the polymer pellets that we buy. So we need to make sure that the surfactants are removed. And the healing potential of the reversible adhesive was significant and can be used for the rapid repair. And every novel joining techniques introduce some processing problems, and one of these problems is process-induced residual strains that we discussed just now, and that needs to be accounted because otherwise our design progression will not be accurate, because as I said, like nearly 40% of the material yield strength was already reached by means of manufacturing. And the experimentally validated computational tools as such that is developed within this particular study, it actually eliminates the costly trial and approach and can be used as an initial guideline for the better design. And the rapid processing and the selective heating potential of EM joining techniques are some of the key factors that qualifies it for large-scale manufacturing. And overall, this work can be easily extended to other thermoplastics, provided the approach used in this work is used to limit the degradation due to EM heating. So you can also see like these are like some of the publications, the journal publications that we got from this particular study. And that is all regarding this presentation. I'm sorry, like I think I took nearly an hour for the presentation. So you guys are open for the questions. So please feel free to ask any questions regarding this.
Yeah, they can raise their hands, and Dr. Suhail will unmute each of them. I think because they don't see an option to unmute their calls, Doctor.
Oh, really? So how do I do that?
You can just press on the name in the participants list.
Okay. So should I stop sharing the screen?
Yes, you can.
Okay. Allowed to talk. I think now.
You just have to select all.
I'm sorry.
Yeah.
Yeah.
Same way they will unmute themselves now.
Okay. So allow everyone to talk.
Okay, they're using their chat instead of. Okay.
So you can also put your question in the chat box so that I can answer them.
Dr. Weil is raising his hand. He just has something to say.
Oh, yeah, sure.
You have to unmute him, Doctor. You're the host now.
Okay. So,
can you hear me?
Yes, I can hear you.
Ah, thank you, Dr. Suhail. Excellent presentation. A lot of information, very detailed. I have one question regarding the reversibility issue. Have you looked into or considered any kind of like a hysteresis like performance of the joint? For example, if you join and join and join, is there any sort of residual unwanted behavior that you're having there. Is there any chance of this? Maybe the question is not correct. Is there a chance that this will happen?
Yes, we have studied that. And so the results that we have got is very similar to the results that we have got from the adhesive as well. So let me share the presentation. So if you see here, like we have, so on the left-hand side, like you have a chart with the y-axis as elastic modulus, and like the x-axis is like different heat cycles. The cycle number 1 for 240C, and then we cool down, and then we gave another cycle of heating, and then the third cycle of heating. And similarly, like you have the toughness properties reduction by the time you reach the third cycle, the second cycle and the third cycle. So this is something that we have clearly observed even with the bonded joints. They increase the strength, but they reduce their toughness property. In other words, yeah, the strength was improved, but they failed much quicker.
Okay. Yeah.
This is something that we have observed with respect to cyclic heating. Like if you heat them, cool them, heat them, cool them, then what happens to the joint strength? But at the same time, there are like other options. Like for instance, like here it is 240C, but from the degradation study that we have finalized is not to heat it until 180C. Sorry, not to heat it until 240C, but only heat it until 180C. So you totally remove the effect of degradation within the polymer. So if you go with the step control heating between 105 and 180, then you can purely get the inherent behavior or the initial behavior of the bonded joint, even if you heat it and cool it. But that paper is still not published. Like we are still working on it.
Oh, great. Thank you. Thanks.
Thank you.
Dr. Naif wants to speak. Please unmute him, Doctor.
Just one. Okay, Dr. I think, yeah, I think Dr. Naif is not unmuted.
Yes. No, he can speak now. Yeah.
Dr. Naif?
Yes, yes, please. Do you hear me?
Yeah, I can hear you now.
Okay, thanks for a nice presentation. Actually, I have simple question about your model. You have a domain of 1 micrometer for, and when you have larger particles like carbon fiber, you have about maybe 1 millimeter.
Yes.
You have 1 micron and we have a millimeter.
Yes.
Why have in between? Why from micron to millimeter? Why you don't have, for example, 20 micron or 100 micron cube for the modeling?
You mean, okay, let me go back. You mean this, are you able to see the slides?
Still not.
Okay, let me share it. Okay, this one, right?
Yes, one micro here and here 1 millimeter.
Okay, the reason why is because like this software, it didn't allow me to have some full-fledged the top fiber. For instance, like, okay, the diameter of this one is like 8 microns, but the length of the short carbon fiber could be like approaching nearly 1 millimeter.
Okay. Why shouldn't it greater than 1 millimeter?
I'm sorry?
1 millimeter exact length. Why shouldn't it be higher than
It could be higher than it could be. So like what I got, like the highest short carbon fiber that I found was like nearly 800 micron, and so I just put 1 millimeter as the size of the RVE, because like if I increase the RVE size, then that means I need to increase the computational time as well.
Yes, but here you have trade-off between the computational time and also the accuracy.
Exactly.
Okay, thank you.
Thank you. So, any more questions? Okay. In that case, thank you very much. Thank you very much, everyone, for your time. I really appreciate it.
Thank you.
Thank you.
Thank you.
Thank you, Doctor. Excellent.